Welcome, everyone. Today, we're diving into an exciting exploration of counting coprime triples and uncovering some fascinating patterns together. Last time, we used the µ-Detector to count pairs of numbers between 1 and n that are coprime by looking at visible lattice points in a grid.
I remember that the formula had squares in it because we were counting pairs, not triples.
We started with the two-dimensional case, using the µ-Detector to pick out exactly those pairs that share no common prime factor.
So the new question is, which triples between 1 and n have greatest common divisor equal to 1?
Exactly. We now care about three numbers at a time and whether they share any common prime factor. Think of all integer points in a cube from 1 to n in each direction, and shine a light from the origin so that only the visible points correspond to coprime triples.
So T of n will play the same role for triples that our old function did for pairs.
Next, we will reuse the same µ-Detector idea, but now apply it to the greatest common divisor of three numbers at once. Here, we let the µ-Detector watch the greatest common divisor of A, B, and C, just like it watched the greatest common divisor of a pair before.
So the detector still says 1 when the three numbers are coprime and 0 otherwise.
This sum runs over all common divisors of A, B, and C. And because of the alternating signs in mu, it equals 1 exactly when the three numbers share no prime factor.
So it really is a yes or no test for the triple being coprime, just like in the two-variable case.
Now we apply the detector to every triple between 1 and n. For a fixed d, the integer part of n over d counts how many multiples of d we can use in one coordinate, and taking the cube counts how many triples of such multiples we get.
Then mu of d tells us whether to add or subtract that whole block of triples in the final count.
The heart of the method is unchanged. We just point the detector at three numbers instead of two. For each possible common divisor d, we group together all triples where every entry is a multiple of d.
Along one axis, that just means we count how many times d fits into the range from 1 up to n.
Right, and because the three coordinates are independent, the total number of triples of multiples is that count raised to the third power. Finally, we let mu of d decide the sign and add these blocks up over all d to produce the exact value of t of n. On the next slide, we plug in n equal to 20 and see which divisors actually contribute to t of 20.
I am guessing only the square-free divisors matter, because mu is 0 on everything else.
Let us apply the formula to n equals 20 and see how the contributions from different d values add up.
There are many divisors up to 20, but I expect most terms will be small or even vanish.
Here is our general formula specialized to n equal 20. So we only need to inspect divisors up to 20.
And we can skip any d where mu of d is 0, because those terms contribute nothing.
If we write out the non-zero terms and simplify, the final total comes out to 6,745 coprime triples. Only square-free d values with at least one multiple between 1 and 20 survive, because mu is 0 on all others. The biggest terms come from small d. The term for d equal 1 counts all 20 cubed triples, and the others subtract or add back blocks where the three entries share small primes.
The signs match the pattern for mu. Negative for primes like 2, 3, and 5, and positive for products of two distinct primes like 6 and 10.
For a larger d, there is only one multiple between 1 and 20, so each such d contributes just plus or minus 1 depending on mu of d.
So about 5/6 of all 20 cubed triples are coprime, which is surprisingly high.
Yes, and in the limit for large n, this proportion settles down to a constant related to the Riemann zeta function at 3. Now that we have seen the triple case in action, we can spot the general pattern for k-tuples and connect it to a clean density formula. The triple case hints at a simple rule for any number of coordinates k.
I am expecting that the square became a cube for triples and should become a kth power in general.
Here, n sub k of n counts k tuples whose entries run from 1 to n and whose greatest common divisor is 1, using the same mu weights but now with a kth power.
So for k equal to 3, this matches our T of n formula, and for k equal to 2, it recovers the pair formula from before.
This limit says that for large n, the fraction of all k tuples that are coprime tends to 1 divided by zeta of k.
So for triples, the density is 1 over zeta of 3, and for pairs, it is 1 over zeta of 2.
As a quick check, try to write down the expression that counts coprime quadruples with entries between 1 and n.
It should be the same summation as before, but with a fourth power instead of a cube.
Exactly. You sum mu of d times the fourth power of the number of multiples of d between 1 and n, one term for each positive d. Notice that each coordinate independently chooses a multiple of d, so the total number of k tuples of multiples is the product of k identical counts, which is why a kth power appears.
That means if we ever jumped to 5 or 10 dimensions, we would just raise that count to the 5th or 10th power.
Plugging in k equal to 3, 1 over zeta of 3 is about 0.832, so most triples are coprime.
For pairs, the density is only about 0.607, so adding a third coordinate actually makes coprimality more common.
We have extended the µ-Detector from pairs to triples, seen how the formula scales to any k, and connected the whole picture to densities given by 1 over zeta of k. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.